Hey guys, we're going to be going over the second part of this lesson, Unit 4, Day 3, Part 2 in your student packet this year, 14 through 17 are the pages. The learning targets are going to be talking about how to use tree diagrams, using the multiplication rule to help with probabilities, and talking about the ones that are at least ones. So grab a calculator and let's get started. If you remember the other day, we played a little game talking about starburst, and the game was in a bag of starburst. We had 4 reds, we had 2 yellows, and the goal was to pull out a red, replace it, and pull out a starburst, see what color it was, replace it, and then pull out another one. And we wanted to see if the probability of winning the game could be calculated. And we ended up getting about 56%. So real quickly, the way that we got that was we had 4 red, we had 2 yellow. So we did the probability of 2 reds is going to be 4, 6 times 4, 6. And then the probability of 2 yellow would be 2, 6 times 2, 6. And those probabilities stayed 4, 6 the second draw because we put it back in the cup. And so it ended up being 16 out of 36 plus 4 out of 36, which ends up being about 20 out of 36. And that's roughly about, I think it's about 0.56. So 0.555. So yeah, we can say about 0.556, 55.6%. And we want to know what would happen if we left the starburst out. How would that change the probability? And most people would think, well, if I took the starburst out as I went to draw my second one, then that probability is probably going to decrease. So let's find out using what we call a tree diagram. So let's look over here at question number 4. In the idea here, we're going to have 4 red and 2 yellow. And in the bag, we're going to reach the first time. The probability of getting the first one being red is going to be 4 out of 6. The probability of the first one being yellow would be 2 out of 6. Now, if we take that draw a second time, you got to remember that we have left out what we drew. So if we draw the first one out, then we only have 3 red left over and 5 total starbursts left over. So it's going to be 3/5. Now, if my second option branches out to be a yellow, so if, I could either be red and then red, or I could be red and then yellow. Well, I still have all my yellows, but I have 1 less total overall. So you got to think about this as 1 less red, and then this number means 1 less total, 1 less overall. So my denominator changes. My numerator might stay the same depending on the situation, if I'm getting another one here. So over here, if I do the first one being yellow, what's the probability of the second one being red? Well, I still have all my reds, but I'm down to 5. And the probability of my second one being yellow is going to be 1 out of 5. So the way that we're going to do this is after you set up a tree diagram with your individual probabilities, this is 100% of this option. These two are 100% of this option, and these two are 100% of this option. We do a multiplication. The word and implies that I want to know what the overlap is. Since we have our probabilities for each one of these, what we want to do here is we want to multiply. And so to get this number, I'm going to take my 4, 6 times my 3/5, which is 12 out of 30. To get this box, I'm going to follow this branch. So I'm going to do 4, 6 times 2 out of 5. And that's going to be 8 out of 30. And then you can see the pattern. 2, 6 times 4, 4/5 is going to be 8 out of 30 as well. And then finally, we're going to have 2, 6 times 1/5, which is going to be 2 out of 30. Now, one thing that you're going to notice is these 4 probabilities at the end. These are every possible outcome, right? Red, 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 yellow, yellow, red, yellow, yellow, in that order. If you add all these up, what do you notice? If I say this plus this plus this plus that, you should get 1. You got 12, 8, that's 20. And then you got 8 and 2, that's another 10. That should be 30, but 30 out of 30. is equal to 1. So these probabilities always add to 1. So your adds give you 1. Your ands always give you 1. So the theoretical probability of winning this game, well, what represents a win in this case? 2 reds and 2 yellows, if you remember from the prior exercise. So we're looking for 2 reds. Well, 2 reds is going to be here. So that's a win. A red and a yellow, that's a loss. And then a yellow and a yellow is also a win. So the probability of winning this game is either this option or this option. So really that's the probability of red and red plus the probability of yellow and yellow, which ends up being 12/30ths plus 2/30ths. And that's about 14 out of 30. So that's a little bit under half. That's probably about 0.47. Let's see. So 0.4667. So we'll just kind of call that that. So that decreased because if you remember, without replacement, or when I put it back in, it was about 55.6%. So it was a little bit higher that way. So let's look at the question now. What is the probability that the first candy was red given the person won the game? All right, I want to think about this question here for a moment. Pause the video, see if you can try it on your own. What's the probability that the first candy was red given the person won the game? All right, so the way that we're going to do this is we're going to say, think about this word given. On the previous video, we talked about what that conditional probability means. So I'm going to put this in symbolic form. The probability first red given we won the game. Well, that's going to look like this, okay? Out of all of your winnings, we had one of them have the first one be red. So we have 2 options here. We got this one here. That's a win, and that's a win. So this is your denominator, okay? These are what it's out of, okay? That's your given, okay? These are your given. Which means those are going to go on your denominator, okay? This is going to be your given. So we want to put on the denominator these 2, your winnings, 12 out of 30 plus 2 out of 30. Now the question was, given that this happened, what's the likelihood or what's the probability that the player got a red the first time? Well, if the player got a red the first time and that player won, the player is going to get a red the second time. So it's really out of these 2, which one represents first one red? It's this one. So your numerator would be what represents the 12 out of 30. So if you notice here, this number right here is stolen from this, right? I'm using this component of it, but I'm using the overall winning. So this is your win. And this is the winnings with the red. Okay, the red one was first, but really it's red, red, or yellow, yellow. So this is the winnings with red out of the total winnings. That is how you calculate it. But we know this is 14 out of 30, so it's really just 12 out of 30 over 14 out of 30. And if you know a little bit about fractions, these 30s will just cancel. So it's really 12 out of 14. And 12 out of 14 is about 86%. 85.7%, so about 0.857. So what another way to interpret that is out of the winners, 85.7% of them had the 2 reds. So I could also ask the question, what's the probability of the winners being the 2 yellows? And that would be the 2 out of 30 divided by 14 out of 30. And that would be 14.3%. But guess what? This number plus that number should add to 100%. So that plus that's your full one right there. Okay. So you could also do this with decimals, I suppose. It's a little messier, but if you do 12 out of 30 we know that that's 0.4. So I could say 0.4 divided by, and my total winnings was about 0.467. You can see there's your 0.857 right there if you round that up. So you could do it that way too. All right, so get that down, and then let's go to the next one. Okay, awesome. So let's talk about flipping coins. Now, on the previous problem, taking that starburst out, let me write this down here. Taking that starburst out renders these being independent. So these are not independent. Because the probability changed knowing what the first one was, okay? Independent, if I throw it back in the mix and shuffle them up and pull it out again, that's going to be the same probability, 4, 6 times 4, 6. But since they're not independent, the probability did change. So similarly here, when you're flipping a coin here, you want to think about, well, does the flip of a coin impact the next flip, right? And the answer is going to be no. When you flip 3 coins, you're going to have basically 8 options, right? Head, 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 HHT, HTH, HET, blah, 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 right? You got 8 options, but where does that 8 come from? Well, it comes from the probability of flipping a coin being 1/2. We know that whether you get heads or tails, it's going to be 1/2. Now, if I get heads, the probability of getting heads again is still going to be 1/2 because the coin doesn't have any memory of what you flipped. Probability of getting tails is still going to be 1/2. And so these are all going to be 1/2. And I'm flipping it 3 times. So since these are all independent of each other, I don't have to worry about changing my probability. And where does the 8 come from? Well, 1/2 times 1/2 times 1/2, or 1/2 to the 3rd power. Right? That's going to be 1 out of 8. I mean, you can look at your sample space. Again, this is your sample space. And you can see, well, I got 8 different options. So I know that 3 heads is going to be a 1 out of 8. So each of these options individually would be 1 out of 8. And of course, they all add to what? Good job. They all add to 1. So 1 out of 8 plus 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 1 out of 8 all add to 1. Of course, this is how you do an independent tree diagram, which really is kind of a waste of the time. But let's answer some questions. Are events A and B independent? Justify your answer using the probabilities from the tree diagram. Yes. The probability of A equals 1/2, and B, probability of B given A, well, it actually should be A given B, but the probability of getting, let me reword it like this. The probability of B is 1/2, right? The probability of B given A is still going to be 1/2. In other words, flipping the coin the first time will not impact the second flip. I mean, we don't really need numbers with that. That's pretty straightforward, right? Just like rolling a dice the second time is not impacted by the first roll, and so on and so on. Replacing a card and then drawing another card out, that same probability would be there if you're looking for the same thing. All right, so let's finish this up. What's the probability of getting a head 3 times? Well, let's see. We got 3 H's, so that's going to be 1/2, 1/2, 1/2. We got 1/8, easy enough. What's the probability of getting a head 2 times? Now, you might read this. I don't like the wording of this question, I'm going to be honest with you. So if I'm looking at it, getting a head 2 times, are we talking about at least 2 or exactly 2? That's a good question. And I'm not really sure what this one's asking. So let's do it both ways. If it said at least 2, well, there's going to be 1, 2, 3, but then there's also this. At least 2 would be 4 because the 3 heads is at least 2. So that's going to be 4 out of 8. but exactly 2 would only be 3 out of it. All right, so the tree diagram is kind of helpful to help us, figure out what those are. And then this last one, given the first toss was a tail, what's the probability of getting at least 1 head? Now your tails, your first toss being a tail, you got 4 options here. So the probability of getting at least 1 head, well, let's see. There's a head. There's another one. There's another one. And, oh, that one doesn't have one. So out of the 4, these 3 have at least 1 head. So it's going to be 3 out of 4. Okay, we don't need to really involve formulas with that if you have your sample space written out. Any questions on that? Awesome, thanks for asking. Okay, next part. And I'm going to take a pause here for a moment. Okay, y'all. Now, before I get into the last question of the notes, I want to talk about the concept of at least 1. And I want to teach it to you using a different thought process, okay? So imagine you have a 6-sided die. You would probably know the probability of getting a 2 on a 6-sided die would be 1 out of 6. And the probability of getting not getting a 2 would be 5 out of 6. Suppose I ask the following question. If you roll the die 3 times, what is the probability that at least one of the rolls is a 2? Now, what you could do on this problem in this scenario is create a sample space. Let's see about what that would look like. All right, so I laid out some possible options here. I want you to kind of take a look at what this all means, okay? If I roll the die 3 times, I have 3 different distinct outcomes for getting exactly 1, 2. I could have the first roll be a 2, and the second and third be not 2s. Remember, these 5, 6 represent your not, okay? And we want to multiply those together because we're repeating those events. But I could have the second one be the 2, or the third one be the 2. Then to get exactly 2 2s, I could do the first and second one being a 2, or the first and third, or the last 2. And to get exactly 3 2s, I only really have one option. They're all going to be 2s, right? So to figure out that probability, I would need to add all these up together and figure out what that equals. Well, let's do a little computation here. So 6 times 6 times 6 will be our denominator, and that's 6 to the 3rd power, which is 216. So that's really going to be 25, 25, 25. Let me multiply that out. 25, 20, that's 75 out of 216. Over here, I have 5 times 1 times 1, so 5, 10, 15 out of 216. And this is going to be 1 out of 216. So if I combine those, 75 plus 15, that's going to be 90, 91 out of 216. That should be the probability of getting at least 1 roll being 2, right? 91 out of 216 is 0.42129, blah, blah, blah. That's a very, very extremely complicated way to get that answer. And never do this on an AP exam or on a question like this, okay? This is how you could get the answer if you knew how to set up your sample space. But let's look into the problem that follows in your notes for a minute. And it'll kind of walk you through it. I'm going to come back to this and I'm going to show you how to answer this using that method, okay? So this is your question, question number 8. People with O negative blood are universal donors. That is, any patient can receive a transfusion of O negative blood. Only 7.2% of the American population has O negative blood, so it's a small percentage. Now, if we took 10 people in a sample, okay, to appear at random to give blood, what's the probability that at least one of them is a universal donor? Now, we're not going to sit out here and do our sample space in this scenario because that's going to be writing that out too many times. 10 people, that's a lot of options to write. So what you're going to do is the following. The probability that an American has O negative blood, well, we know that's 0.072, right? That's given to us. B, the probability that an American does not have O negative blood is going to be 1 minus 0.7072. That's the complement probability, and that's going to be 1 minus 0.072, which is 0.928. Now, the probability of something not being O negative, out of that sample of 10, just not being O negative is going to be the probability of the complement of O negative, right? So hold on a second. So that would be the 0.928. I guess I put that in the wrong spot. Oops. So that's going to be down here. So 1 minus 0.072 is going to be 0.928. Now the concept of at least one, if there is not at least one universal donor out of 10, if there's not at least one, how many would there be in the sample? If there's not at least one, okay, if I don't have at least one, I'm going to have how many? 0, okay? None. The probability of there being none is the complement of the probability of at least one, okay? So let's think about how we can approach this problem. The probability of at least one O negative is 1 minus the probability of none of the 10 being O negative. Now, gosh, I can think that's got to be a lot easier to calculate, right? The probability that none of the 10 are being O negative, and it is, because what you're going to do is you have the none, right? You have the complement of O negative. So what you're going to do for that part is you're going to say, all right, well, I got that 0.928. See, I'm going to multiply 0.928 times itself 10 times. Wait a minute. That's a lot of multiplication. I think I know exponents, my friends. All right, we got 10 of them. 0.928 to the 10th power. All right, what is that? Put that in your calculator. That's about 47.367%, 0.47367. All right, so let's think about this problem now. The probability of at least one O negative is the complement of none of the 10 being O negative. That's going to be 1 minus this. And of course, that's 0.5263. So 52.63%, we could expect about 52.63% of the sample of 10 to have at least one O negative donor. Now let's go back to this problem here for a moment. All right, this is more of a realistic approach problem to talking about people coming in donating blood, trying to calculate that probabilities. But let's go back to our die example. Okay, I really want to see if this makes sense now. All right, if you roll the die 3 times, what's the probability that at least one of the rolls is 2? Well, again, we know the probability of getting a 2 is 1/6 and not getting a 2 is 5/6. So the probability of at least 1 2 out of 3 is the same as 1 minus the probability of none of the 3 being a 2. Okay? 1 minus the probability of none of the 3 being the 2. So what's the probability of not getting a 2? That's 5/6, right? You can have 1, 3, 4, 5, or 6. So none of the 3 would be 5/6 raised to the 3rd power. Now we're going to subtract that from 1. 5/6 to the 3rd power. 5/6 in parentheses, raise it to the 3rd. That's 0.5787. Now, subtract that from 1. 0.42129. 0.42129. 6. All right, look at this. That's all we needed for that. Versus that. Which one do you prefer? At least one. 1 minus the probability of none. That is how you do that. All right, guys, let's summarize. So let's do the important ideas. Then we'll do a little check your understanding and we'll pause to check that, okay? So let's go back to our important ideas and just fill in a couple things. This is your tree diagram. I'll make sure all of them add to 1. And then remember, as you're going along, the probabilities can change if they're not independent of each other. Let's look at the multiplication rule. The general multiplication rule for AN is just multiplying, but remember, take into account their conditions, okay? If the probabilities do change, you wanna change those denominators. Now, if A and B are not independent, that's gonna be the case. But if they're independent, then we don't have to worry about that condition changing, right? They're gonna be equal to each other. So it's just gonna be times each other, okay? Where in this case here, you're always going to be the one outcome could be affected by the other, so they could change. The at least one is 1 minus the probability of none in your sample. In a tree diagram, you want to label the probabilities on each branch. Compute the AND probabilities at the end of each path. All the branches along the path are going to be multiplied. Make sure all the AND probabilities at the end of the path add to 1, okay? Now, you have some check your understanding questions. And you and I both know you ain't going to get much out of this unless you try them on your own. So pause this video, try on your own. And once you finish, work these out, you can unpause it and check with me. Welcome back, guys. I hope you got a chance to read through this problem. A computer company makes desktop, laptop, tablet computers at factories in 2 states, California and Texas. The California factory produces 40% of the company's computers, and the Texas factory makes the rest. Of the computers made in California, 25% are desktops, 30% are laptops, and the rest are tablets. Of those made in Texas, 10% are desktops, 20% are laptops, and the rest are tablets. All computers are first shipped to a distribution center in Missouri before being sent out to stores. Suppose we select a computer at random from the distribution center and observed where it was made and whether it is a desktop model or laptop. Well, here's your tree diagram. See if that matches up with what you have, and I'll make a couple notes on here. First, we were told that 40% of the computers came from California. Now, we were not told specifically that 60% of the computers came from Texas, but you got to calculate that because you know that it's one or the other. So California or Texas. We were also told the percent of laptops and desktops. We were also told the percent of laptops and desktops for Texas. So it's implied that you have to figure out this percentage because these all add to 1. So 1 minus 0.25 plus 30, is going to give you 0.45. 1 minus 0.1 plus 0.2 equals 0.7. Okay, so we know that that's going to be 0.7, 0.45. We know that's going to be 0.6. We get all our options, and at the end of the day, we're going to multiply. So all your ands get multiplied. Now, your tree diagram doesn't need a lot more words on it, right? You don't need to say probability of computers in California. It's implied. So if you want to just multiply them and get these numbers and make sure they add to 1. That's your tree diagram. Now look at question B. Find the probability the computer is a tablet. Well, if you look at your options here, the computer could be a tablet in 2 different spots. There and there. So the probability of a computer being a tablet would simply be the sum of these two, 0.18 plus 0.42. Symbolically, you would say tablet given California, tablet given Texas, but we already got those calculations from our tree diagram. So you don't need to recalculate those if you've already shown that work up here, okay? Add them together and you get about 0.6, 60%. Letter C. If we select 4 computers at random from the distribution center with replacement, so we're putting them back in, so we're not changing up your outcomes at the end. What is the probability that at least one of the computers is a tablet computer? So let's look at your at least one. We know that 60% are tablets, right? So the way that at least one is always going to be the 1 minus the probability none are tablets. Now, what probability of these are not tablets? That should be 40%. So what we're going to do is we're going to take that that 60% from 1 to get 40%. It's a sample of 4. So that's going to become your exponent, right? 0.4 to the 4th power, which ends up being, if you put it in your calculator, 0.0256. That's the probability that none of them are tablets. So the probability of at least one is 1 subtract that. So you get about 97.44%. 97.4% of the time in a sample of 4, you're going to find at least one of them being tablets. Finally, our last question. Given the tablet is selected, so this is a conditional, what's the probability that it was made in California? So our tablets are 60%. Given that it was a tablet, what's the probability from California? We're looking at the ands for Californian tablet. And if you go up to the end of your tree diagram, that's 18%. The 60% can be broken down from the 18 from Texas and 42, or 18 from California and the 42% from Texas, right? That combined gives you your 60%. So it's really 18 out of 60, 18% out of 60%. And when you do that division, you're going to get 0.3. So there's a couple ways to interpret that. You can say, given, you could just basically write the problem out, and given that it was from that a tablet was selected, 30% chance of it being made in California, or you could simply say 30% of the tablets are from California in that scenario. Well, guys, I hope this was helpful. Thanks for watching. Y'all will have a review session next class, and we'll go over some of the different probability rules and do a little bit more practice before we leave for the break. Thank you.